One type of homogeneous equation that we will be encountering very quickly in the course is a second order homogeneous equation with imaginary roots. So let's start by finding our test solution, and that's going to be CE to the RT, and we can insert that into our differential. This would be good if I inserted it. Our second derivative of our CE to the RT is going to be C R squared E to the RT plus 4C E to the RT to complete our equation equals 0. The C's will cancel out, the E to the RT will cancel out, and we get R squared plus 4 equals 0. So our roots are R equals plus or minus 2j. Now, I hope to prove to you that these actually specifies not two exponentials, but sines and cosines. So let's put our solution together here. And let's use two constants. We're going to call it CA e to the 2jt plus CB e to the negative 2jt. And we can now use Euler's. And we can now distribute our constants. And now we can combine these terms using trigonometric identities. So we want to remember that the cosine of negative theta is equal to cosine of theta, and the sine of negative theta is equal to negative sine theta. So now we can make our changes. We're going to have a minus because we're using this identity for the sine. And now we can collect terms. Now, CA plus CB is just a constant, and CA minus CB is a different constant. And when we are using this process for a homogeneous equation, we can consider J as any number, and we can absorb that into our constant for the sine term. So we can redefine our constants. C1 cosine 2t plus C2 sine 2t. Now, if you don't believe me that this actually works, take this solution, put it back into the differential equation, and you should come up with 0.